We were asked, in which limits below can we use L'Hopital's rule? L'Hopital's rule, also called Bernoulli's rule, uses derivatives to evaluate limits involving indeterminate forms. The most common indeterminate form is 0 divided by 0. However, if a limit fits any of these indeterminate forms, L'Hopital's rule does apply, which states the limit as x approaches c of f of x divided by g of x equals the limit as x approaches c of f prime of x divided by g prime of x. And the idea is this limit will be easier to evaluate than the original limit. But again, we can only apply L'Hopital's rule if the limit is in one of these indeterminate forms. If it's not in one of these forms, we cannot apply L'Hopital's rule. So going back to our exercise, we will only be checking to see if L'Hopital's rule can be applied. We will not be determining the limits. Looking at this first limit, we have the limit as x approaches c of sine 6x divided by 6x. As x approaches 0, sine 6x approaches sine 0, and 6x also approaches 0. And because sine 0 equals 0, this limit is in the indeterminate form of 0 divided by 0, and therefore L'Hopital's rule can be applied. Now if needed, we can verify sine 0 equals 0 by using the unit circle or the graph of the basic sine function. On the unit circle, sine theta is equal to y. Here's 0 radians on the unit circle. Notice at this point, the y-coordinate is 0, verifying sine 0 is 0. Or looking at the graph of the basic sine function, which we should recognize here, notice that sine 0 does equal 0. Next, we have the limit as x approaches pi over 7 of cosine x divided by the quantity 7x minus pi. As x approaches pi over 7, cosine x approaches cosine pi over 7. And the quantity 7x minus pi approaches 7 times pi over 7 minus pi. Looking at the denominator, 7 times pi over 7 is pi minus pi is 0. But now looking at the numerator, cosine pi over 7 does not approach 0. It's approximately equal to 0.9, and therefore this limit approaches cosine pi over 7 divided by 0, which is not one of the indeterminate forms, and therefore L'Hopital's rule does not apply to this limit. Next, we have the limit as x approaches 0 of 6x divided by cotangent x. As x approaches 0, 6x approaches 0, and cotangent x approaches cotangent 0. Now let's determine the value of cotangent 0 using the unit circle, as well as looking at the graph of the cotangent function. On the unit circle, remember tangent theta is equal to sine theta divided by cosine theta, which should be y divided by x, and therefore cotangent theta is equal to x divided by y. So looking at 0 radians here, notice how the point on the unit circle is 1, 0, and therefore cotangent 0 is 1 divided by 0, and division by 0 is undefined, and therefore this is in the form of 0 divided by an undefined value, which does not fit one of the indeterminate forms of L'Hopital's rule, and therefore L'Hopital's rule does not apply. Also, if we look at the graph of the cotangent function, which we should recognize here, notice as we approach cotangent 0, from the positive side or right side, we approach positive infinity. From the left or negative side, we approach negative infinity, which again verifies that cotangent 0 is undefined. And we also have a vertical asymptote at x equals 0 radians. And now for the last example, we have the limit as x approaches 3 of the quantity x minus 3 divided by natural log of the quantity 4 minus x. As x approaches 3, x minus 3 approaches 0, and natural log 4 minus x approaches natural log 1. And natural log 1 is equal to 0, and therefore this limit is in the indeterminate form of 0 divided by 0, and L'Hopital's rule does apply. If we look at the graph of the basic natural log function, we can verify natural log 1 equals 0. Here's a graph of f of x equals natural log x. Notice when the input or x value is 1, the function value is 0. I hope you found this helpful.